Any extra? Okay. All right, so good afternoon. In case you're wondering, as a distance student, why we are starting late, it's because we were actually having a quiz. I'm not going to go through the solution of the quiz because we have some of the distance students online right now. Maybe next time I'm going to just explain what the solution is. All right, so we are going to continue our lecture on power converter modeling. So as I explained last time, the reason that we want to model a converter is because we are trying to control a converter. The reason that we have to control a converter is because we want to provide line and load regulation, and we are going to become familiar with this terminology a little bit later, what I mean by line and load regulation. In a simple word, we want to, for instance, make sure the output voltage of our converter is always constant no matter what the load is and no matter what the input voltage is, something like that. All right. So we discussed, as we discussed last time, when we tend to analyze or model a converter, first we do a DC analysis. This is to find out the operating point or the operating conditions of the converter. In other words, we will find out what is the DC value of the current that is passing through the inductor? What is the DC value or average value of the output voltage? Those kind of things. Or what is the typical or kind of DC value for the duty cycle of, for instance, 40% or something like that. And then we start perturbing our converter around that particular operating point, and that's why we call it the small signal model. So first we do some sort of a DC analysis, and then in a DC way we realize our converter is operating pretty much like a transformer. However, we had a question last time, a valid question, how come we are using a transformer even though our signal is a DC? This is a common thing that everybody does in the textbook, so we are going to follow the same thing. Although, if you really want to be really accurate, you shouldn't apply a DC signal to or DC voltage source to a transformer. So basically, a better way of representing this would be using dependent sources. And this would be D times IL. So if you want to be super accurate, you got to use dependent sources because transformers are not used for DC signals. But in almost every textbook that you open up, there is actually a transformer being used. So that's the common practice that we do. So we also call this an average model. The reason is so actually we had a question last time at the end of the class, what is an average model? So this is the average model basically. The reason that we call it the average model is it is taking the switches out and representing the switches using the average behavior of the switches basically. So on average, the voltage that appears here, from here to here, is the value of the duty cycle times the input voltage, as I said, on average. In reality, it's actually a square-shaped waveform, but on average, it's like a DC signal with D times Vn. Or on average, the current that, this is all, by the way, this is all a buck converter. On average, the current that is drawn from the source is the duty cycle times the inductor current. Again, on average. In reality, it's actually a kind of a, in reality, it's something like this. But then we represent it with like an average value of the signal. So what's the advantage of doing this? If you're simulating a large signal, let's say, for instance, you are simulate a large system, like you're simulating, for instance, an IEEE 38 bus system. You have a lot of basically nodes and a lot of math going on, and you have a bunch of converters connected to that system, for instance, as, I don't know, solid state transformers or something like that. If all of these solid state transformers have detailed models and all of the switches are turning on and off and things like that, your simulation is going to take forever. So a lot of times you basically get rid of the switches. Remember, switch calculations need a lot of resolution. So you basically get rid of your switches, you represent them with their average behavior, and therefore you can actually increase the time interval between the samples that your software has to calculate. So your simulation gets a little bit faster, basically, something like that. But then again, you have to remember this is the average model, so it only predicts the average behavior of the converter, not the switching behavior of the converter. So for the sake of simplification, a lot of times, if you have a lot of converters and you are only caring about the average behavior of the system, then you represent them with the average behavior. Now, I put IL over here. So IL is by basically representing the current that is drawn on the output side. You can either represent it with an inductor and a capacitor and the load, or even further simplified with just a resistor, something like that. So this IL is just the current. It's not really a current source. All right. So, so we do a DC analysis. Then once we pay attention to all of our signals, we realize most of our signals are relatively DC with a small signal perturbations. So that's how we define these as small signal perturbations. So anything that is perturbation, I'm actually using a hat on top, trying to emphasize on the fact that this is a small signal perturbation. And because it's a small signal, it is much smaller than the original DC value of the signal. All right. So once I write the top two equations that I had, one of them was Vx is Vn times d, which is basically this equation over here in a more generalized way. And the other equation is the input current is duty cycle times the inductor current or the pole current. So once I write these two equations and replace all of the signals with their DC value and a small signal perturbation values, I end up with two terms that I can delete. One of them is this one, because I have two small signals multiplied by each other, so they are both small. Again, multiply them by each other, they even get smaller, and I can eliminate. And the same thing over here. In other words, I'm linearizing the system. Basically, when you have two signals multiplied by each other, you can linearize it by making it in a form of one of them is constant, the other one is multiplied by that one, and the second one is constant, and the first one is multiplied by the first one. So that's actually what we are doing over here. All right. So now what I'm going to do is, once I have these two equations, and again, I'm taking the DC parts out. So I already know that the DC value of Vx is duty cycle times the DC value of the input voltage, or the DC value of the input current in the buck converter is the DC value of the duty cycle times the DC value of the inductor current. So I already know that. I don't really have to basically draw it in my circuit. So I only care about the perturbations basically when I draw an equivalent circuit model. Okay. So the equivalent circuit model looks like this. So have these two equations in mind. All right, so this is basically taking care of this term over here. Then I have another current, which is capital D times basically IL. Again, I'm going back to the bad habit of using a transformer. This is going to be this current. All right, this transformer, the turns ratio of the transformer is 1 to D. And on the input side, we have small signal perturbations of the input voltage. And on the output side of the transformer, or on the secondary side of the transformer, we have, so I have to build up this top equation. For instance, I have to take care of this term over here, and then this term. All right, so this is what's going to look like. And these are voltage terms, so I'm using voltage sources. All right. And this voltage over here is already D times V in perturbed. This is because on the input side of the transformer, I'm actually on the primary side. I'm putting the input perturbations of the input to the primary side, so it multiplies by D and appears on the secondary side. So that part is not a surprise. So I took care of these two terms. And then you got to draw the rest. So this gives you basically perturbations in the inductor current. And then you can draw the rest of the system. Okay. All right. So, so this circuit model that I just drew is the small signal model representing the behavior of the buck converter. So this is a small signal model for the buck converter. Okay, so it is a time invariant model. In other words, independent on what time it is, none of the parameters or the structure of the system varies. We got rid of the time variancy when we represented the average model as opposed to the switching model, because switches are time dependent. Sometimes they are on, sometimes they are off. When we take the switches off and replace them with the average behavior of a switch, you are getting rid of the time dependency in the system. Then the model was not linear originally because two of my signals, duty cycle is my control input. Later on we are going to see what I mean by that. And input voltage is a source of perturbation. So two of the inputs to the system are being multiplied by each other, and that's a non-linearity. And we kind of linearize the system. So this model is linear time invariant basically. So we started from the buck converter, which is a time variant topology and nonlinear. We kind of linearized it and got rid of the time variancy. Please remember that in this small signal model, we are relying on the DC operating point of the converter. This is a DC value. It's a number, for instance, 5 amperes. This is the duty cycle, for instance, I don't know, 40%. These are all constants. This is the DC value of the input voltage. And this model doesn't give you the DC value of the input voltage or the DC value of the output voltage. This model tells you if I, for instance, perturb the input voltage and analyze this network, how much of a perturbation appears on the output side. So this model only predicts you that. It doesn't tell you your output voltage is 20 volts or something like that, because you already have to find out what your output voltage is or what your input voltage is before even getting to this point. So do not expect it from this model. If you're simulating it, do not expect it from this model to give you, sometimes it does, sometimes it doesn't. So pretty much it's a good idea not to expect any DC value getting out of this model, basically. All right. So remember, this was for the buck converter. Now I'm going to generalize this and into a single, a small signal model for a single pole double throw switch. All right. So in a general case, if I have a single pole double throw switch, I just label this to be throw number 1, throw number 2, and the pole, I call this the pole current, and obviously this is the throw voltage. Okay, I always assume the top throw is positive, the bottom throw is negative, and the pole current is actually flowing to the left. And also duty cycle has to be determined. Duty cycle is defined based on the top throw. Obviously, if top throw is a diode and the bottom throw is a switch, then you have to do 1 minus duty cycle. No problem there. So based on the analysis that we had, this anywhere that I have or identify this structure, now I can just take it out and plug in equivalent to this, which is basically this model. All right, something like that. I mean, some people don't put this, some people do. I would say it's better, good idea to do it, basically. And what is as a control input? Changes in the duty cycle is all we can do. We can change the duty cycle to accommodate, a particular objective in the system, or to satisfy a particular objective. All right, so I would like you guys to kind of remember how this thing looks like. You don't really have to memorize it, but just have a sense about what it looks like. So it includes a kind of a DC to DC transformer with a turns ratio of 1 to D. And on the input side, we also have a dependent source of current, which is proportional with the DC value of the pole current. So remember, you have to do DC analysis first to find out this, and this. And then afterwards, you can actually replace it with this small signal model. Any questions? Yes?
Why do you say that it's VT1 minus VT2?
It's up to you. So that's actually our throw voltage. So I'm just going to replace it with the throw voltage. The DC value of the throw voltage.
The input voltage would be normally constant, right? So why need to consider perturbation around?
Oh, the input voltage is not actually constant. For instance, if you have a battery as your input voltage, the real voltage of the battery is dependent on the state of charge of the battery. So it varies a little bit. And there might be other components connected to your input voltage. So, okay, why is it that the input voltage is constant? Here is why. Let's say this is a battery, but the battery also has an internal resistance. And then you have a load, and then you have your DC-DC converter. All right. So depending on the what kind of load you have actually here, like for instance, your load is a pulsating load, then you realize this voltage from here to here, because of this internal resistance, is also a pulsating voltage. So the input voltage is not constant, and sometimes you have two converters cascaded with each other. So the input voltage of the second converter is the output voltage of the primary converter, and then there is some ripple in there as well.
What I want to say is like input voltage is not what we can control. So
Okay.
So in the equation before, it doesn't make it non-linear when input voltage is multiplied with T.
Okay, it is not something we can control, but it is it's still an input to the system. It's a disturbing input to the system. So it is still an input. So the inputs to the systems are, and we're going to see them in a few minutes, variations in the input voltage, variations in the load current, variations in the duty cycle. These are all the three inputs to the system. The only one that we can control is the duty cycle. The rest of them is out of our control, but they are still inputs. All right. Good questions? Any more? Okay. So, so for the sake of practice, let's use this model to, for instance, and apply this model that we just developed, this small signal model, to a boost converter. Now, before doing so, let me make sure, highlight over here, that we have to develop this model after DC analysis. Okay, so keep this model in mind, and we are trying to develop one for the boost converter. All right, so let's go back to the schematic of the boost topology, and I'm actually drawing it in the standard form. That throws are on the left, the pole and the inductor are on the right. And throw voltage is positive because the output voltage is positive. Okay. The only difference or something that we are not familiar with is D in the boost converter is determined by the conduction situation of the bottom switch. So I have to do 1 minus D over here. So this is the only tricky part. So remember, in the boost converter, the bottom switch is an active switch, and based on that, the duty cycle is defined. However, in our original definition, duty cycle is always representing the conduction of the top throw. So we just have to invert it. So we call it D prime. In a lot of books, you see D prime is 1 minus D, basically. The other thing that we have to remember is if I perturb the duty cycle, and if I perturb 1 minus the duty cycle, because 1 doesn't get perturbed, we realize this equation holds. That perturbations in the duty cycle is the opposite of perturbations in D prime. In other words, if the duty cycle increases, 1 minus D decreases, so they're actually going the opposite ways. So all I have to do is just take a look at the top schematic and just replace it over here. So now our control is renamed as D prime as our control input times IP, and this is IP DC value. Okay, and this is T1, this is T2, and we have our transformer. 1 to D prime here, because D prime is basically replacing D in this topology. And then the dependent source of D prime perturbed times VT1 minus VT2 and then the rest of the system. So this is P. All right, something like this. Then we can work with this a little bit. For instance, we can get rid of VT1 minus VT2, or we have IP over here. We don't know what that is. So this is VT, by the way. Or we are not comfortable working with D prime, so I can redraw the circuit and basically clean it up a little bit to this form. And by the way, this is IP, the pole current over here, is actually the opposite of the input current, right? IP is the opposite of the input current. So there's a negative sign involved. Also, D prime perturb is the opposite of D perturb. So there are two negative signs involved. I just get rid of both of them. And write it in this form, okay? And again, let's say I don't really like the duty cycle. I'm sorry, D prime, so I just try to get rid of it wherever I see it. Then this polarity changes because D prime perturb is the opposite of D perturb. So there's a negative sign there. I just flip the polarity of my dependent source over here. And VT1 minus VT2 is nothing but the DC value of the output voltage. Okay. And the rest is the same. Okay. All right. Any questions? So this model or this circuit diagram is telling me if I'm interested in, for instance, if I perturb the duty cycle, if I perturb the input voltage, how much of that perturbation appears in the output voltage? Now I have a circuit that can actually predict that, okay? Also, for the third converter, let's do it for the buck boost topology. It's a little bit more complicated. Let's just do it over here to have all three classic converters next to each other.
I have a question.
Sure.
How did we change from D prime perturb to D perturb in that input side of the part? I mean, there is a negative, positive, I guess.
Okay.
But I didn't get the logic. Can you explain it?
Okay, so generally speaking, D and D prime, D plus D prime is 1, okay? So if I perturb one of them or increase one of them, the other one decreases. So in terms of perturbations, they are the opposite of each other, all right? So I start with D prime because D prime is actually the real command in the boost converter. And my model, you can see D prime appears everywhere. There's a D prime as a DC value, D prime as perturbation, and another D prime as perturbations. So this is the very first draft of my model. Then I can say, okay, D prime is a little bit confusing. I just want to eliminate it. And wherever I have D prime, I can just replace it with negative D. So I can replace, if I have a lower, if I have a perturbed D prime, I replace it with negative D. If I have a capital D prime, I replace it with 1 minus D. All right? So this is how we get this. The other trick that I did, so there's a negative sign here, for instance, and that negative sign causes the change of polarity here. There's a negative sign here, and it should potentially change the polarity of this current. However, at the same time, pole current is flowing out, input current is flowing in. So there's a negative sign here as well. So again, the negative times negative, I don't have to change the polarity.
How is there a negative signs towards the input side?
Towards the input side, you mean the negative sign here, change the input side voltage?
I cannot see. I mean, where are you pointing? You said there is a negative sign towards the input side of the
input current. The input current and pole current, depending on the direction and polarities that we have defined for them, are opposing each other. So whenever I have perturbations in the pole current, or the DC value of the pole current is the opposite or negative of the DC value of the input current. So that negative, the second negative, so there's a negative sign here multiplied by another one, so I don't really have to do this.
So the input current is opposite direction to the pole current.
Exactly, exactly. So remember, pole current is always flowing from left to right, flowing out. The input current is the current that you're drawing from your DC source. So it's representing how much power you're drawing from your source. They're opposing each other in this case.
Professor,
Yes.
but that pole current is not the inductor current in this case, is it?
The pole current is the inductor current. Now, you may say, I want to stick with the inductor current instead of using the input current. Then there's a negative sign here that you have to consider. So it depends on, are you sticking with the input current or the inductor current? So I can redraw this. Okay, I can say, okay, pole current. Oh, wait a minute. The inductor current and the input current are the same. So
Yes.
never mind what I
Okay.
said. Okay. Yeah, okay. So yeah, in terms of direction, inductor current and pole current and the inductor current and the input current in the boost converter are the same. Okay. Other questions? So these things could be a little bit confusing at the beginning. Once you use them a few times, for instance, for the coming homework assignment, you will get good at it. Assuming that I can get rid of all these red marks. Well, obviously I can delete them to a certain point. All right. Okay, so this was for the boost converter. Let's exercise it one more time and one last time for the buck boost converter, okay? So I'm going to draw the buck boost converter in its classic form. All right, if you remember from earlier discussions, again, we always tend to draw the throws on the left side, pole on the right side, inductor current should go out, or the pole current basically should go out, I'm sorry. And this would be a representation for the buck boost topology, okay? Now, again, all I have to do is just identify this structure over here and replace it with the model that we developed over here, basically. And then clean it up just a little bit. For instance, if VT1 minus VT2 appears, I have to identify what that is in my buck-boost topology, or if there is IP appearing there, something like that. Okay, so let's do it. IP, so remember this is IP. IP is always flowing from left to right. And by the way, D, this is our active switch, and D is determined by that, so no problem, and we don't have to mess with D prime at all. So this is 1 to D. Okay, we throw 1, again these are average values, we throw 1 minus we throw 2 turns out to be V in, basically this voltage from here to here, which is V in plus V out. All right, so there is no negative sign involved. Let me clean these a little bit. And that's it, the rest of the network. All right, something like this. So I guess the trick over here is, now if you go back to any of those complicated converters in that paper, once you identify a single pole double throw switch, then you can take or unplug that switch off and plug it in with the equivalent small signal model, basically. So that's the trick. This is what I'm trying to basically ask you guys to learn. First, look at the topology, identify the single pole double throw switch or switches, and then replace that network with the small signal model equivalent in case you're interested in the small signal model for your topology. So here I didn't read right again, but anyway, I pole is not the input current, is not the output current. I pole is the opposite. Again, depends on what you define as your inductor current. Let's just call it I-pole, okay? Because if I put it inductor current, then it may become a little bit confusing. All right. So, question?
Actually, how do we get D times IP between T1 and T2? Because
This comes from the original model that we had. So if you see from T1 to T2, this is still T1, and this is still T2. From T1 to T2, we have a current source, a small signal current source drawn, proportional with the pole current, and the primary side of the transformer. That's always true. Now for the buck converter, between T1 and T2, we also have the input voltage source connected. For the boost converter, we have the output voltage connected. For the buck boost, we have nothing. It's just T1 plus T2, T1 and T2.
Professor, how would small signal analysis help us in a practical design?
Okay. Well, we are going to see. So as I said, when we are trying to design a controller, like if you are trying to, for instance, design a PI controller or a PID controller, once you have information about the dynamic behavior of the system, then you can, for instance, get the fastest PID controller possible. And we are going to actually see probably next week sometime how it's going to help us with the design.
Is there a difference between H-space averaging and these methods?
No, all these modeling approaches are pretty much end up with the same transfer functions. There are minor differences, but I would say I don't see a significant difference between the averaging that we are doing it here and the state space averaging. They will end up with equal transfer functions. Okay, questions? All right. To answer Venkat's, or to follow up on Venkat's question, why do we even do this? And we had the question about transfer functions. So let's talk about transfer functions. Okay. So once I tell you I have a linear time invariant system available, the first thing that comes to your mind is the Laplace transformation and transfer function. So that's what we are doing over here. So if I try to kind of in a block diagram represent my converter as we talked about it a few minutes ago, so for instance, it's any of these circuits, you can see that if I perturb the input voltage, the rest of the system is going to be perturbed. So it's like it's actually one of the sources. The other one that is not very obvious is if I perturb my load resistance, the rest of the system is going to be perturbed. Okay, if you change the load resistance in any of these systems, you can see it's going to have some impact on the rest of the system. However, we do not really represent perturbations in the load resistance by R represented with the current of the output, I load. This is more general because on the output side, you may not have a resistor. You may have another converter. So whatever current that load or whatever that is, it is drawing, or it is another source of our perturbance. The other one is the duty cycle. So these are the inputs to my system. We call this the control input. Because it is something that we can control or the controller can control. And these two guys are out of our hands, so these are basically disturbances. All right. Then we have an output voltage. Okay, which is a function of all of these perturbances, basically, depending on what converter we are looking at. Okay. Now, almost all the times, your output voltage is the voltage across a capacitor. So if you want to actually make it even more general, you can argue that, and we had a question about the state space. Inductor current is another state. So let's call it F1 of, and this is F2 of. All right? But sometimes the inductor current doesn't really matter. For instance, it doesn't directly matter. For instance, if you are doing voltage mode control, we are going to see what it is later. We don't really measure the inductor current. We have nothing to do with the inductor current. Inductor current is there, but it's more like an internal parameter. We don't really care about it. We don't measure it. But when you're doing current mode control, inductor current actually does matter because you have to measure the inductor current and then directly control the value of the inductor current. So sometimes it is an output, sometimes you don't care about it and you don't consider it as an output. Now, in most of the textbooks, unfortunately, this is going to get a little bit confusing. Instead of Vn, they write it as Vg. Okay? So I don't know, G stands for generator or whatever it is. A lot of places, in a lot of books, they use it Vg. And I load and I out are the same, so this part is not confusing. All right. So we are identifying our system has 3 inputs, 1 output, or in a more general case, 2 outputs. Now, and we know that this is the small signal that we develop is an LTI system. So now I can say I have 3 inputs, and I'm interested in the output voltage. Because it's a linear time invariant model, I can use superposition. For instance, I can assume the other 2 inputs are 0 and only perturb one of them and see what happens to the output voltage. Then I perturb the second one and keep the first and the third one 0. And finally, perturb the third one and keep the first and second one 0. And that's how you get the transfer functions. So these transfer functions are labeled in a standard way. And by the way, when we talk about transfer functions, we are talking about the Laplace transformation. So all of a sudden, I'm switching from a time domain kind of a notation to frequency domain notations. So I won't perturb the duty cycle. In other words, I keep it constant. And I won't perturb the load current or keep the load constant, only perturb the input voltage and then see how much of a perturbation appears in the output voltage, okay? So I call it GVG. This is called line to output transfer function. And sometimes it's called audio susceptibility. That means if you have some noise on the output, how susceptible your output voltage. If you have some perturbations or some noise in the input, how susceptible your output is to that input noise. It's called audio susceptibility. Then we have another transfer function that we use often, which is Z out, or the output impedance basically. There is a negative sign here, please pay attention. The reason there is a negative sign is, the output current is going out of the converter. It's not actually going into the converter. So that's why we have to make sure there's a negative sign here. All right, so we keep the other 2 inputs constant. Duty cycle is constant or not perturbed. The input voltage is constant and not perturbed. I only perturb the current that my converter is drawing, my load is drawing, or in other words, I'm basically manipulating with the load and see how that would affect the output voltage. So it's called the output impedance. If you are curious about why we care about the output impedance of our converter, the answer is when you have 2 converters cascaded, if you go back to the stability analysis and things like that, you realize there should be a certain condition satisfied between the output impedance of the upstream converter and the input impedance of the downstream converter. So that's why we care about it. And finally, the third transfer function, as long as the output voltage is concerned, is called the control to output basically transfer function, which means if I perturb the duty cycle what happens on the output side. So we keep the input voltage constant, the load constant, only perturb the duty cycle, and see what happens in terms of perturbations in the output voltage. So these notations are standard. So GVG, you have to remember what it is. Line to output transfer function. GVD is control to output transfer function. Let me write it over here. And obviously the impedance. So in case you're wondering where these notations come from, so this G, which is representing the source, appears here, and this D, which represents another control input, appears here. And the voltage over here appears here and here. So this is where these notations come from. All right. So having this structure in mind, now I can redraw my system using like a block diagram to redraw my system. So remember, these are all transfer functions. So quite a very simple kind of a superposition kind of a thing. So from a controller standpoint, this is the model for our DC to DC converter, whatever it is, buck converter, boost converter. So this is the small signal model. All right. And now, because we are trying to control the system, for instance, we are trying to regulate the output voltage. So what we do is we add a controller. We measure the output, like a feedback thing. We measure the output voltage, we feed it to the controller, and then, for instance, make decisions for the duty cycle. All right. So our objective for the next couple of sessions is, what is this controller? How can we come up with basically a transfer function for this controller and things like that? Now, if you want to write it down, and sometimes it's helpful to write it down, I'm just going to write it. We can argue that the output voltage is nothing but GVD times perturbations in the duty cycle plus GVG times perturbations in the input voltage minus Z out times perturbations in the output current. And by the way, please note that there's a negative sign here. This is because we defined there was a negative sign we introduced in Z out, definition of Z out, and that's why we have to put this negative sign over here. All right. So what we got to do now is, so this is a very kind of a block diagram representation of our system as long as we have a small signal model available. Now, You may ask, okay, I have this Bach topology and I'm curious to find, for instance, GVG for this Bach topology. What should I do? So let's do it basically. And this is very similar to your homework assignment. For your homework, you have to do it for the boost topology basically. So for instance, you have this Bach topology. And you are trying to find what is the audio susceptibility transfer function for this Bach topology, okay? So technically we are looking for how is the output voltage is affected by changes in the input voltage while the load current is not perturbed, or the load resistance is not perturbed, and also the duty cycle is not perturbed. So we are trying to find out what this is, basically. All right. So we have to go back to the small signal model that we had for the Bach topology. What was the small signal model? We just drew it a few minutes ago. This is Vn perturbed. We had D perturbed times IP. Then we had this transformer, R1 to D. And this dependent source of voltage, D perturbed times Vn. Okay, so where did I get this? I just got it from the first small signal model that we developed, which was basically this one over here. So this is the same thing. IP and IL are the same, by the way. Okay, so this is the general model, but I'm only interested in one transfer function, and that is when the input voltage is perturbed and the load current is fixed and the duty cycle is fixed. So this will go to 0 and this will go to 0. All right? So actually my small signal model gets simplified if only I'm interested in GVG. So the bottom line is you are down to this very simple circuit. All right. So going back to circuits 1, remember this has again, this is all in the S domain, okay, Laplace transformation. This impedance is Ls. This is 1 over Cs. This is R. So you can easily say this would be, so it's like a divider of a basically impedance divider. The whole thing is timed D times Vn perturbed. All right, so this is coming back from circuits 1. So I'm going to stop here. We are running out of time. So I'm going to continue on this transfer function, plot it in a Bode plot waveform, and then we have a table that represents a lot of canonical form. In a canonical form represents all these transfer functions, okay? And then we are going to go and design a controller for this topology. All right, I'll see you guys on Thursday.